Take a flashlight, point it outward, and imagine there exists a place where that light still moves at light speed, but it can never get farther away. That sentence sounds like a trick. Light is the champion of escape. It doesn't get tired. It doesn't need fuel. It doesn't slow down. If anything in the universe can get away from a bad neighborhood, it should be light. So what could it possibly mean to say, the light is moving normally and yet it can't escape? If you've ever heard the usual story, you've probably been handed a picture like this. A black hole is a cosmic vacuum cleaner. It pulls too hard, so everything gets sucked in, even light. The problem is, that picture is secretly doing two dishonest things. First, it treats gravity like a kind of super-strong tug that just wins by brute force. Second, it suggests there's a place where the rules suddenly change and light just gives up. But physics is at its best when you don't let it get away with phrases like gives up. Light doesn't give up. Objects don't decide to fall. Nature doesn't know our metaphors. What it does have are rules, very stubborn ones, and if you push those rules far enough, you get consequences that look spooky from a distance. So let's do this the Feynman way. No sacred vocabulary at the start. No, trust me, it's curved spacetime as a magic spell. Just a couple of rules you already accept, and a few thought experiments where you and I agree on what we would measure. Here's the deal. A black hole is not primarily an object. It's not a thing that eats. The heart of it is much cleaner and much stranger. A black hole is a region where the geometry of spacetime is arranged so that every possible later you can have points inward and no later points outward. That sounds abstract, so let's earn it step by step. Start with escape, because that's the word that keeps coming up. What does escape mean in ordinary life? If you throw a ball straight up, it rises, slows, stops, and falls back. You didn't escape Earth because you didn't start with enough speed. If you throw it harder, it goes higher and comes back. Harder still, higher still. There's a very specific speed where something changes. If you launch it above that speed, Earth's gravity can tug on it forever, and it still never returns. It keeps coasting away, slower and slower, but always moving outward. That speed is called the escape velocity. Notice something important. Escape is not about whether gravity exists. Gravity exists everywhere. Escape is about whether your initial motion is enough that gravity can't reverse it. It's a competition between what you start with and how much gravity can take away. Now on Earth, that escape speed is about 11 kilometers per second. You don't need to memorize it. The point is, it's a finite number. On the Moon, it's lower. On Jupiter, it's higher. The more massive and compact the object, the higher the escape speed. And now a simple, dangerous question. What if you had an object so compact that its escape velocity was equal to the speed of light? Because light has a speed limit. In fact, it is the speed limit. The outside observer's information is constrained by global signal propagation, and it explains why black holes are not universally destructive at a distance. Their distant gravitational field is not stickier than anything else of the same mass. What matters is whether you wander into a region where the future itself becomes one way. So here's a final thought experiment to lock it in. You're hovering far from a black hole with a spaceship. You have fuel. You decide to dip closer, then fire your engines and come back out. You can do that. You can do a close flyby. You can even orbit. The fact that a black hole exists does not trap you by mere presence. Now you decide to dip closer still. You want to find the exact place where the rules change, but there won't be a sign. Your instruments will measure increasing tidal effects, increasing redshift of signals you send outward, increasing difficulty in hovering. You might notice that to hover at a fixed radius, you need to fire your engines harder and harder. That's a clue. Hovering is not free fall. Free fall is what you get when you stop resisting. To hover, you need acceleration. At some radius, maintaining a hover would require infinite acceleration, an unphysical demand. That is another face of the horizon, the impossibility of remaining stationary there. Then you choose to fall freely. You cross. Locally, your clock ticks, your flashlight works, your equations in your small cabin still look like physics. Yet from that moment, there is no outward signal that can reach the outside. The turnstile has been passed. Not because you were grabbed, but because the set of futures that connect to the outside no longer includes you. That is what the horizon really is. If you carry that idea into the rest of physics, you start seeing why horizons show up in more places than you'd expect. There are cosmological horizons in an expanding universe, where distant galaxies recede so fast that light emitted now will never reach us. There are horizons in accelerated frames. There are analog horizons in certain fluids and condensed matter systems that mimic aspects of the mathematics. Physics keeps drawing lines that separate can influence from cannot influence. When you focus on causality and information flow, many puzzles become sharper. And that might be the best outcome of understanding black holes. Not just now I know a cool cosmic fact, but I have a new way to think about what a physical explanation even is. Because the deepest explanations in physics are often about constraints, not about what nature wants to do, but about what nature is allowed to do. Light's speed limit is a constraint. Causality is a constraint. The way space-time responds to energy and momentum is a constraint expressed in geometry. Put those together, and the black hole stops being an exotic monster and becomes an inevitable possibility. There's still wonder in it, maybe even more wonder. The universe isn't mysterious because it hides its rules. It's mysterious because its rules, when taken seriously, imply structures that our everyday instincts were never built to anticipate. So next time someone says a black hole is where gravity is so strong even light can't escape, you can gently upgrade that sentence. You can say light isn't failing. It's obeying the rules in a space-time where outward is no longer part of the future. And if you want to end with a question that physics hasn't settled, here's one that's both humble and thrilling. If horizons are boundaries of what can be known from the outside, then what is the most honest thing we can say about what exists beyond them? We can build theories. We can test their consequences outside. We can detect shadows and rings and waves. But the interior remains a place where nature challenges our best frameworks to agree with each other. That's not a reason to be gloomy. It's a reason to stay curious. The horizon isn't just a line around a black hole. It's a reminder that in physics, the boundary between understood and not yet can be sharp. And the only way it moves is when we learn to ask better questions. Nothing with mass can reach it, and nothing can exceed it. That rule isn't a preference. It's baked into how cause and effect works. If you could exceed that speed, you could arrange events so that effects happen before causes in some frames. The universe doesn't allow that. So if escape means leave without being turned around, and the escape speed at some radius is the speed limit of the universe, then at that radius you've hit a boundary. At that distance from the center, there is no faster option. There is no just launch harder. The best you can possibly do is move at light speed, and that's exactly the speed you'd need just to barely not be pulled back. What would light do there? In the naive Newtonian picture, you'd say it would be right on the edge. It would travel outward, but gravity would take away its outward motion just fast enough that it never increases its distance. It would hover like a climber stuck on a slope where every step forward slides back. That picture is not the full truth. General relativity is the full truth for gravity in this regime, and it doesn't treat light as a little projectile losing speed. Light always moves at c locally. That's one of the profound differences. Still, this escape speed equals c argument is a good motivation because it points to the right kind of boundary, a place where getting out would require you to do the impossible. General relativity gives that boundary a crisp name, the event horizon. Not a surface you hit like a wall, not a membrane you can scrape. It's a boundary in space-time that separates events that can send signals to infinity from events that can't. Infinity here doesn't mean forever. It means the faraway outside world. If you're inside, no signal you send, no light pulse, no radio transmission, no scream encoded in neutrinos can ever reach the outside. Now pause and ask, if light can't get out, does that mean gravity is infinitely strong there? It's tempting to think so, but that's exactly the misconception the title is daring us to unlearn. Here's a counterexample that breaks the infinite pull cartoon. There are black holes with masses millions or billions of times the sun's mass, supermassive black holes. Their horizons are enormous in size. If you cross the horizon of a supermassive black hole, the tidal forces at that boundary could be small enough that you might not notice anything dramatic at the instant you cross. You wouldn't necessarily be torn apart right there. Nothing would explode. Your coffee wouldn't instantly fly off the table, Locally, the laws of physics in your small region would still look like the laws of physics in freefall. So if the horizon can be locally gentle, what makes it special? The answer can't be the pull is infinite. The answer has to be something more global, more about the structure of what paths are possible. Let's make that concrete with a mental picture that doesn't require equations. Picture yourself in an airport with one of those long, moving walkways, the kind that helps you get to your gate faster. Now imagine a weird airport where the walkway is moving toward a pit, and the closer you get to the pit, the faster the walkway moves. You can still walk. You can walk forward or backward. You have a maximum walking speed. That maximum is like a speed limit in your own little world. If the walkway is moving slowly, you can easily walk away from the pit. If the walkway moves faster, you can still escape as long as you can walk faster than it carries you inward. But there will be a line, an exact location, where the inward motion of the walkway equals your maximum walking speed. At that line, you can walk as hard as you want outward, and you will simply stay in place relative to the airport. You are walking at your personal speed limit, and the ground under you is moving inward at the same rate. You're not failing. You're not being sucked. It's just that the rules allow only so much outward motion, and the background is carrying everything inward. Then there's the region past that line. Inside it, the walkway is moving inward faster than your maximum walking speed. Now there is no possible action that leads you outward. You can still walk outward. You can still try, but every step of outward is overwhelmed, and your net motion is inward. Your choices have been reduced by the environment. Not because you're weak, but because the rules and the background motion together leave you no outward option. That is the feeling of an event horizon, not literally a walkway. Space is not a conveyor belt in the everyday sense, but it captures the key idea, a boundary beyond which outward is no longer an available future. Now take that analogy and sharpen it so it's not just emotional. What is the physical walkway in the real universe? It's not a material surface, it's space-time geometry, specifically how light cones tilt, meaning how the set of possible future directions for a particle or a light ray is arranged. Let me say that in plain language. At any moment, you have a set of possible next moments. You can choose to step left, right, forward, backward. If you're wearing a jetpack, you can choose more options. If you're walking, fewer options. But one thing is fixed. You can't choose a next moment that requires you to move faster than light. That's your absolute limit. So visualize, not space, but your tomorrow arrow. The arrow that points from you, now, to you, a moment later. That arrow has to point into the future, and it has to stay within the allowed speed limit. In normal space, there are tomorrow arrows that point outward from any location. There are also tomorrow arrows that point inward. You can choose to go either way. Near a black hole, those arrows tilt. The geometry is such that the allowed future directions become more and more biased inward. Outside the horizon, you can still pick a tomorrow that increases your distance from the center. You can still run away. It might take effort. It might require rockets, but it's possible. At the horizon, the last outward-directed light ray that can just barely hover is the dividing case. It is, in a deep sense, the final outward tomorrow that isn't really outward anymore. Inside the horizon, every allowed tomorrow points inward. Even light's tomorrow points inward, not because light slows down. It doesn't, but because outward has stopped being a direction that fits inside the set of allowable futures. If you're tempted to say, but outward is just a direction in space, how can it stop existing? Good. That's exactly the discomfort that tells you you're near the real idea. We're used to thinking that directions in space are fixed. North is north, outward is outward. But relativity asks you to separate what is locally true from what is globally inevitable. Locally, you can always set up a coordinate system where you feel like you're floating, where light behaves normally, where physics looks like physics. Globally, the structure of spacetime can still be arranged so that all paths you can take lead to a certain fate. A black hole is that kind of fate. It's not a monster that reaches out and grabs you. It's a region where the map of possible futures funnels you inward. Now, if that's what the horizon is, we can revisit one of the most famous statements people make. To an outside observer, you freeze at the horizon. Is that true? Yes, in a certain carefully defined sense. Is it the whole story? No. And if you only hear that version, you might think the horizon is a place where time literally stops. Let's do the measurement game. You are falling toward a black hole. Somewhere far away, your friend has a telescope and a clock. You also have a clock and you have a flashlight. You agree on a simple protocol. Every second, by your own clock, you send a pulse of light back to your friend, 1 pulse per second, like a heartbeat. What does your friend see? As you fall deeper, the light you send has to climb out of a stronger gravitational field. In general relativity, climbing out means the light gets redshifted. Its frequency decreases. The puissance else is spread out in time. Your friend receives your 1-second pulses as 2 seconds apart, then 5 seconds apart, then a minute apart, then an hour apart. Your clock appears to be running slower and slower. At the same time, your image dims. The light is stretched and weakened. Eventually, from your friend's point of view, your pulses become so delayed and so redshifted that you effectively fade away. Your friend never receives a signal that says, "I crossed the horizon at this instant." It's not that you can't send it. It's that the geometry ensures that such a signal cannot arrive. From far away, you do appear to freeze and fade at the boundary. Now switch perspectives. What do you experience? If you are freely falling, you don't feel a special jerk at the horizon of a large black hole. Locally, you are in free fall, and free fall feels weightless. Your clock ticks normally. You keep sending your pulses. You cross the horizon in a finite amount of your own time. Nothing locally screams, "This is the line." There's no painted stripe in space. So how can both of these be true? How can you cross in finite time while your friend never sees you cross? The trick is to remember what seeing means. Your friend doesn't have access to your local experience. Your friend only has access to signals that reach them, and the horizon is by definition the boundary beyond which signals to the outside stop being possible. So the freezing is not a physical event happening to you. It is a statement about what information can propagate outward. It's a statement about communication, not about your body becoming suspended. This is where a second analogy can help, one that's less about motion and more about one-way rules. Picture a one-way turnstile in a subway station. On one side of the turnstile, you can walk back and forth. Once you pass through, you can still move around, you can still walk, you can still do normal things, but you cannot go back through the turnstile. The turnstile is not a wall that crushes you. It's not a force field that makes your legs stop working. It's just a boundary in the rules. This direction is allowed, that direction is not. The event horizon is a turnstile for causality. Before it, your future includes paths that lead outward and influence the outside. After it, your future does not include any path that influences the outside. And if you're thinking, okay, but why does the universe have such a turnstile at all? That's the big question. The honest answer is because general relativity allows space-time to curve in such a way that the light cones tilt inward. The horizon is the point where the outward edge of the cone stops intersecting the outside world. That's a very geometric statement. You don't have to love geometry to accept it. You can test it by asking what light rays do. Light defines the causal structure. If you know what light can do, you know what information can do, and you know what possible future means. Now there's another piece people usually mix into this, the singularity. The word singularity gets treated like a monster at the center, an infinitely dense point where physics ditches. Sometimes it's presented like the black hole is literally a hole in space, and at the bottom is an infinite abyss. Be careful with that. The singularity in the simplest black hole solutions is a place where the mathematical description predicts infinite curvature and breaks down. It tells you that the classical theory is being pushed beyond its valid range. It's like using the equations of fluid flow and getting infinite pressure at a point. It means your model needs new physics there. So do black holes have singularities? In classical general relativity, yes. Gravitational collapse leads to a region where the theory says the curvature becomes unbounded. In real nature, we expect quantum gravity to modify that story. We do not have a finished quantum gravity theory that we can confidently apply. So the intellectually honest position is, the horizon and the external behavior of black holes are well described and tested. The deep interior and the ultimate fate at the center are still frontier territory. But you don't need to solve quantum gravity to understand the horizon. That's the part people often miss. The event horizon is not a speculation. It's a consequence of the causal structure in a spacetime that behaves like a black hole, and our observations increasingly match that picture. Still, you might ask a very practical question. What actually forms a black hole? Do they just exist as strange objects, or do they come from something? They form when matter collapses so much that the region becomes compact enough that escape becomes impossible. For a star, the story is a fight. The star's gravity wants to compress it. Pressure from hot gas and radiation wants to hold it up. For most of a star's life, those forces balance. When the star runs out of fuel, the pressure support weakens, the core collapses. For some masses, you get a white dwarf supported by quantum pressure. For higher masses, a neutron star. For even higher masses, there is no known stable pressure that can stop collapse, and the star continues inward. If enough mass is packed into a small enough radius, an event horizon forms. Notice the logic. You don't need infinite gravity to form a horizon. You need enough mass in a small enough space that the geometry reshapes the set of possible futures. The horizon can form while the matter is still collapsing. It's not like the star becomes a hole first and then collapses into it. The horizon is part of the evolving space-time. At this point, you might wonder, if the horizon is so gentle for a supermassive black hole, why do people talk about spaghettification, being stretched into noodles? That's tidal forces. Gravity is stronger closer to the mass. If your feet are closer than your head, gravity pulls your feet more strongly. The difference is what stretches you. Tidal forces depend on how quickly gravity changes with distance. For a small black hole, the change is very sharp near the horizon, so tides can be enormous at the boundary. For a huge black hole, the horizon is far from the center, and the gradient can be mild there, so you might cross the horizon of a supermassive black hole without dramatic tides. The stretching becomes severe deeper inside, where the gradient increases. This is another way to see why infinite pull at the horizon is the wrong picture. If it were infinite, you'd always be destroyed at the boundary, but nature doesn't work that way. So what does the black hole do to the outside universe if not suck? Here's a fact that sounds boring, but is actually profound. From far away, a black hole's gravity can look just like the gravity of any other object with the same mass. If the sun were magically replaced by a black hole of the same mass, the Earth would keep orbiting almost the same way. You wouldn't instantly get pulled in. The danger is not that a black hole's gravity is uniquely sticky at a distance. The danger is that if you get close enough, you enter a region where escape becomes impossible. It's the boundary condition that changes, not the distant pull. Now let's talk about what a black hole looks like, because this is where many explanations either get too mystical or too artistic. If the black hole itself emits no light, how can we see anything about it? We can see what it does to light around it. We can see matter swirling near it, heating up and glowing. We can see stars orbiting something invisible. And in recent years, we can literally image the shadow that general relativity predicts. That shadow isn't the black hole as a dark ball. It's a silhouette created by the way light is bent and captured. Think of light from behind the black hole trying to reach us. Some rays pass near the black hole and get deflected like a lens. Some pass too close and get captured, spiraling in. The boundary between the rays that escape and the rays that don't creates a dark region in the image, what we call the shadow. When the Event Horizon Telescope produced that first image of M87, people sometimes said, "We photographed a black hole." The more careful statement is, we photographed the emission around the black hole and the shadow pattern consistent with an event horizon and strong lensing. The image matches the expectations from general relativity remarkably well. What's important for our unique explanation is not the pretty picture. It's what the picture is testing. It's testing the idea that there is a boundary in the space-time where light that goes in doesn't come back out. That's a causal statement. And black holes don't just sit there quietly. Sometimes they merge. When two massive objects orbit, they disturb space-time. That disturbance propagates as gravitational waves, ripples in the geometry itself. Here's an everyday anchor. Sound is a ripple in air pressure. You don't need air to be moving as a whole for sound to travel. A wave is a pattern. Gravitational waves are a pattern in space-time geometry, propagating at the speed of light. When LIGO detected gravitational waves from a merger in 2015, announced in 2016, the signal had a characteristic chirp rising frequency and amplitude as two massive objects spiraled closer, then a final ringdown as the merged OBJ settled. The masses inferred were in the range expected for black holes. The waveform matched general relativity's predictions astonishingly well. So we have two different kinds of evidence, light bending and shadows on one hand, and space-time ringing on the other. They come from completely different measurement methods, yet they tell a consistent story. There are compact objects with properties matching black holes. Still, the title isn't Are Black Holes Real? The title is No One Explains Black Holes Like This. That means the payoff is not just evidence, it's understanding. So let's return to the opening paradox, a place where light moves at light speed but can never get farther away. You're holding a flashlight. You shine it outward. Locally, right there at your hand, the photons move away from you at c. They don't hesitate. They don't crawl. They behave perfectly normally. So how can they fail to increase their distance from the black hole? This is where your intuition about distance and time needs an upgrade. In curved space-time, what counts as increasing distance to the faraway world is not a simple local statement. It's about the global structure of the geometry. Think again about the walkway. Your feet are moving relative to the ground at your maximum speed. Locally, you are doing everything you can. Yet, relative to the airport, your distance to the pit does not increase because the ground is carrying you inward. In the black hole case, the equivalent carrying is the fact that all the allowed future-directed paths are tilted inward. Even a light ray that tries to go outward is confined to paths that ultimately head inward. If you want one crisp sentence to carry away, here it is. A black hole is not a place where light slows down. It is a place where outward is not a direction you can travel into the future. Now you might reasonably object, isn't that just wordplay? You're changing definitions. No, it's not wordplay. It's a different kind of statement about what's possible. Physics is full of these. The second law of thermodynamics isn't just about temperature. It's a statement about what processes are possible and which are effectively impossible. The speed of light limit isn't just about fast objects. It's about what causal connections are possible. The event horizon is in that family, a boundary in what can affect what. Let's make it even more operational. Suppose you cross the horizon and you immediately fire a powerful rocket outward. What happens? If you're outside the horizon, a powerful enough rocket can, in principle, get you out. It might require absurd fuel, but the idea makes sense. Your future can include outward paths. If you're inside, no rocket helps. Not because your rocket fails, but because even at your maximum possible speed, always less than c, the set of future-directed paths you can take does not include ones that reach the outside. Your rocket changes which inward path you take, and how long it takes in your proper time before you reach whatever fate lies deeper, but it cannot create an outward connection to infinity. A neat way to feel that without formulas is to imagine a map where the arrows of possible next steps are drawn at every point. Outside, some arrows point outward. At the horizon, the last outward arrow is tangent. Inside, all arrows tilt inward. You can choose among arrows, but you can't choose an arrow that isn't there. That's not mystical. That's geometry plus a speed limit. And once you truly accept that, a lot of black hole language becomes clearer. For example, point of no return. People hear that and think it means if you cross the boundary, you'll be pulled so hard that you can't turn around. That's a force picture. The real meaning is, if you cross, no signal you send can ever return to the outside. It's about causal connection, not about turning around like a car. Now let's address another common question that creeps in. If nothing can escape, how can black holes evaporate with Hawking radiation? Good question, and the honest answer is, Hawking radiation is not light being emitted from inside the horizon and escaping. That would violate the causal boundary. The idea, in simplified terms, is that quantum fields exist everywhere in space, including near the horizon. In quantum theory, what you call particles can depend on the observer and the background geometry. Near a horizon, the distinction between vacuum and particles becomes subtle. Hawking's calculations showed that from the perspective of faraway observers, black holes should emit a thermal spectrum, as if they have a temperature. That means they lose mass over time. This is a place where we must be careful, because popular explanations often describe virtual particle pairs popping into existence, one falling in and one escaping. That story can be a helpful cartoon, but it is not the real mechanism in a strict sense. The deeper mechanism is about quantum field modes in curved space-time and how the presence of a horizon changes the relationship between past and future states. What you can safely take away is this. Quantum physics plus horizons predicts radiation that carries energy away, so black holes can, in principle, evaporate. For astrophysical black holes, the temperature is extremely low, far lower than the cosmic microwave background for many of them, so the effect is incredibly tiny and has not been directly observed. But it is a serious theoretical prediction that is widely studied. Here's where the story becomes a genuine frontier. If a black hole evaporates, what happens to the information about what fell in? Does it disappear? Quantum mechanics, as we understand it, is uncomfortable with information destruction. General relativity, in its classical form, seems comfortable with horizons hiding details forever. Putting them together produces what people call the black hole information problem. And if you're hoping I'll now reveal the final answer, here is the most Feynman-like thing I can say. We do not yet have complete agreement on the resolution, because we do not yet have a complete quantum theory of gravity that we've tested, the way we've tested, say, electromagnetism. There are strong ideas, and there is progress, but the story is not finished. That's not a failure. That's the living edge of physics. The horizon is a clean concept in general relativity. Hawking radiation is a clean concept in quantum field theory on curved space-time. The full reconciliation is where the deep mysteries still live. Now, before we end, let's make sure the promised aha is actually sitting in your head as something you can use. A black hole is a region where space-time is arranged so that every possible tomorrow you can take leads deeper in and no tomorrow leads back out. If you say that out loud, you can hear how different it is from "it sucks everything in." It's not about appetite. It's about the shape of possibility. It also explains why black holes are so hard to talk about without confusion. Our language is built for objects in space. We like surfaces, forces, impacts, speeds. But the horizon is a boundary in causal structure, more like the edge of a map where certain roads stop existing. It also clarifies why there is no dramatic moment at the horizon for you in freefall. The horizon is not a place where local physics must explode. It is a place where global connections change. Your experience is local.